Hello and welcome everyone. My name is Péter Vörös. I'm an assistant professor at the Eötvös Loránd University, Budapest, Hungary, and in this presentation I'm going to talk about our latest results with implementing a hybrid next-generation NodeB. First of all, let's talk about the GMB user plane requirements. The transition between the uplink GTP and the downlink RLC packets has to be done with encapsulation or decapsulation, which can be easily written down in the P4 code. The GTP tunnel endpoint ID determines the transfer bearer, so we have to set the underlying MAC layer accordingly, which can be implemented with match action tables in P4. We also have to maintain the PDCP sequence number, which is an incremental counter to be able to handle reordered packets, identify duplicates, or missing packets. This is done by register array in P4. We also need to be able to handle ciphering and integrity check, because in the downlink direction, the PDCP payload is encrypted and on the uplink it's decrypted. However, currently P4 programmable switches are not equipped with crypto engines, so this has to be handled with external services. Automatic repeat request, or ARQ, is required for RLC, which ensures reliable data transport via this mechanism to downlink direction. All the outgoing packets are stored until they are acknowledged or the resubmission timeout is reached. Storing these packets in the memory for retransmission is currently not supported by Traffic Manager and Buffering Engine. Let me explain our proposed hybrid design. It all begins with an incoming packet. In the downlink direction, we have to remove the GTP header first, construct the RLC plus PDCP headers, encrypt the payload, then clone the packet, send one out, and send the other packet to the buffering service. Now, let's take a look at the uplink direction. First, we have to decide if it's an RLC status message or an acknowledgement. If it is, we have to stop buffering the acknowledged packages. If not, then we have to decrypt the payload, remove the PDCP plus RLC headers, rebuild the GTP header, and then send out the packet to the uplink port. Take a closer look at our buffering service. When we start buffering a packet, we put it into a ring buffer, store its ID in a hash table, and when the resubmission timeout is reached, we check if the ID is still found in the hash table. If yes, then we clone the packet, send one out, and put one back into the ring buffer. If not, then we free the packet, because this means an RLC acknowledgement has been received. Our hybrid GMB implementation consists of two parts. One, highlighted in this image, that can be programmed in P4. In our case, we use the store this barefoot Tofino-based hardware switch to run this part. On the other hand, there are some parts that cannot be directly programmed in P4 due to the previously shown limitations. These elements can be programmed in DPDK using an x86. With the previously described testbed components, we run several measurements to prove the effectiveness of our hybrid implementation. P4 hardware switches are capable of line rate packet processing, so the only bottleneck can happen at the external services. We did measurements with different number of cores and packet sizes with our buffer service. As you can see on the left image with blue line, we show that 128 byte packets can be processed at around 8 million packets per second rate with just one core, which is around 9 gigabits per second shown as the right image. And it increases almost linearly with the number of CPU cores, so we can say that this external service scales well with the number of cores. However, if we increase the packet size to 1048 byte packets, then we reach the network card's maximum at 2 cores. To conclude, we have a working and scalable hybrid GMB implementation for the user plane functions using P4 and DPDK. Thank you very much for your attention. Feel free to contact me if you have any questions or suggestions. Thank you.